come to the central definition of this course, the definition of a manifold. This notion is of central importance that we are not going to give just one definition, but in our customary style, we are going to give several definitions at once and prove they are all equivalent. Now, before we get to the definition, we must first understand what is it that we are trying to formalize by a definition. Typically, we have some intuitive pictures in mind and we try to capture that in the form of a rigorous mathematical definition. So the general definition that captures our picture is somewhat sophisticated and technical, and the necessity of such a general definition will be completely opaque to you at this stage. So the definition of a manifold is in general a separable metric space, or even a second countable or paracompact Hausdorff topological space that is locally Euclidean. Now this is a bunch of technical terms. You have already come across separable metric space. Locally Euclidean will be fairly easy to define, but I am not sure whether you have come across second countability or paracompactness. So the necessity of such a technical definition, it will be somewhat unclear to you at this stage. So rather than focus on this general notion of a manifold, we will focus on manifolds that are subsets of Rn. Okay. A manifold is an object that locally looks like Euclidean space. What I mean by that is, if you zoom into that manifold with a very high power microscope, you will not be able to distinguish it from an ordinary piece of Euclidean space. We are not interested in general topological manifolds, which are those objects that just locally look like Euclidean space, but we are interested in manifolds on which we can do calculus, that is where we can integrate and differentiate. So these will be manifolds that have some notion of smoothness built into it. Okay, so we will restrict ourselves to what are known as CK smooth manifolds that are embedded in Rn. So embedded submanifolds of Rn is what we will consider. But since these are the only manifolds that we consider, we will just use the term manifold rather than the extremely elongated phrase embedded submanifolds of Rn. Examples of manifolds include cylinders, spheres, ellipsoids, and even somewhat exotic figures like the Mobius strip, which is a one-sided surface. So since we are dealing only with manifolds that are subsets of Rn in this course, we don't need to impose any technical condition like separability or paracompactness. In fact, seeing manifolds in this special setting will pave the way when you do a further course on general smooth manifolds as to why such conditions are necessary. These conditions are automatically inherited in our case. Okay, so I said before we formalize, we need to have a picture of what is it that we want to formalize. The pictures you should have in your mind are that of spheres and ellipsoids and cylinders. So how do you capture something that looks like a sphere or an ellipsoid or whatever? Well, we already have one straightforward answer, and this is an implicit answer. Implicit, or let me use green for definitions. These are provisional definitions. So we have an implicit notion of manifold, which is a subset S of Rn that is locally a hypersurface. So this is a subset which need not be globally defined by one single function, but near the vicinity of any point of S, we should be able to find a function that is whose level hypersurface is going to be exactly this set. Okay, so a subset that is locally a hypersurface. We have already studied these global hypersurfaces, and we have now shown that they behave exactly the way we think a surface should behave. They have well-defined normals, they have well-defined tangent spaces, and so on. Okay, now this is an implicit definition simply because at each point the surface will be described by an equation whose zero set is this piece of this surface. But we have seen that the moment you have a well-defined normal or whatever, you immediately have the implicit function theorem that will give you the second definition, graph. The graph definition, a subset S of Rn is a manifold is a manifold if it is locally the graph. It is locally the graph of a smooth function. Graph of a smooth function. So the first implicit definition deals with equations, the second one deals with graphs, and the first definition immediately gives rise to the second definition, okay, since we have the implicit function theorem. Now graphs, as we have seen in the proof of the lemma that the hyperplane is in fact an n-1 dimensional and so on, immediately gives rise to a parametrization. This was the map capital G which we had defined in that lemma, that is the parametric form, the parametric definition. A subset S of Rn is a manifold if it can be locally parametrized. It can be locally parametrized by a smooth function. So one definition implicit immediately leads to the graph definition, immediately leads to the parametric definition. So our intuitive idea of capturing something that locally looks like a piece of Euclidean space on which we can do calculus has resulted in 3 provisional definitions. Which one do we choose? And how do we make these precise? These are provisional, not fully rigorous definitions. How do we make this precise? Thankfully, all 3 definitions give rise to the same notion, and you can take any one of them as the definition of a manifold. Okay, so let's move on to the definition of a manifold. In fact, definitions of a manifold. So we have 3 definitions. Definitions of a manifold. Okay, so we start with the non-empty set. In this course, we will not be considering empty set as manifold for the time being. A non-empty set M subset of Rn is said to be a d-dimensional CK manifold if one and therefore all of the following 3 conditions is satisfied. Okay, so I must mention D is 0 less than or equal to D is less than N. Okay, we will talk about n-dimensional manifolds sitting in Rn as part of the definition. They are just open sets. So the first condition is for each point in M, we can express M as a graph near A. We have to make that precise, and this is going to look somewhat extremely overly complicated notation. The reason why I'm going to put this overly complicated notation is because a graph just means that some variables can be expressed as a function of the other variables. I want to make that precise once at least, and after that we will generally not be so extremely pedantic. So for each point A in M, we can find an open set. W in Rn such that A is in W, and an open set V subset of Rd, and a function and a CK smooth function f from V to Rn minus D such that M intersect W is precisely the graph of f. So far so good, intuitively clear, not too many technicalities. Now I'm going to make precise what is the meaning of M intersect W is the graph of f. More precisely, we can find d integers. We can find d integers 1 less than or equal to I1 less than I2 less than less than ID less than or equal to n. So you can find d integers I1 to ID and a bijection sigma from 1 to n minus these d integers I1, I2 ID to 1 to n minus d. Keep this in mind. So there are exactly d integers I1 to ID. So if you remove that from 1 to n, you will be left with n minus d integers. You just map these n minus d integers bijectively onto 1 to n minus d. So the definition is we can find such integers and a bijection such that something happens such that denoting f as f1 to f1 comma fn minus d. Remember, f was a map from an open set V in Rd to Rn minus d. So there will be n minus d coordinate functions such that denoting this we have x equal to x1 xn is an element of M intersection W if and only if x I1 x I2 comma xid is an element of V and x sigma of j is nothing but fj of xi1 comma xid whenever j is in 1 to n minus I1 id. Okay, this looks to be a impenetrable fortress of a definition, but it's just making precise what it means for a set to be a graph. Well, what is it saying? In the simplest situation, what we will have is the first d variables would be the independent variables and the final n minus d variables will be the dependent variables, and this function set M intersection W would be written as a graph of the first d variables. But life is not so kind. The dependence could be very complicated. It could happen that the dependence is on the first, third, fifth, seventh variables and so on. So what we do is this I1 to ID gathers together all the independent variables. Okay, I1 to ID gathers all the independent variables. So the rest of the variables is supposed to be the variables that are going to be written as a function of these d variables. Okay, now the function f is going to be the function that writes it as a graph. So the function we are denoting by f1 to fn minus d. This sigma map just puts this f1 to fn minus d in the correct slots to make it a graph. And we have made that precise by saying that a point x1 to xn is there in M intersection W. First of all, the independent variables should belong to V. So you look at all the I1, I2 dot 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 id coordinate of this x1 to xn and you check that it's there in V. Okay, so the independent variables are in fact in V. Then you have to check that the dependent variables are in fact in the dependent variables in fact match with the values of the function f, and that you do by checking that x sigma j is nothing but fj of xi1 to xid. Okay, so indeed it is happening that the dependent variables are arising as the functional values of this function f. Therefore this M intersection W is indeed a graph. So we have made precise what it means for M intersection W to be a graph, and admittedly this is a very ugly thing, but it's somewhat elegant if you think about the way we have formalized. Okay, so this is one definition. The second definition is the one where you have it directly as the level set of a function. So for each a in M, we can find an open set W subset of Rn and a CK smooth map. Let's say G from W to R. So this is going to be a somewhat more general thing. G from W to R n minus d. So far we consider only hypersurfaces that will just give you n minus 1 dimensional manifolds. Now we want to consider level sets of functions whose codomain is not just R but R n minus d. Okay, so we have a map G from W to R n minus d such that M intersection W is the level set of course I must mention A is in W is the level set of G at 0 and rank of dgx. Rank of dgx is n minus d on all points of M intersect W. Okay, so usually what happens is we consider only codomain R, so things become rather simple in that situation. Here we have codomain n minus d. In that scenario we had d to be n minus 1 and n minus d to be 1, so just the gradient non-vanishing is same as saying rank dgx is equal to n minus d, which in that case was 1. Here we have to specify that rank dgx is n minus d. That means it's a full rank matrix. We will see a little bit more about what this definition is trying to say in a moment. Let me just finish this and give the third definition. For each point A in M, we can find an open set. We can find an open set W subset of Rn and a CK smooth map H from U to Rn, where U subset of Rd is an open set and H maps U bijectively onto M intersect W Furthermore, we want the rank of DHX to be equal to D this time, not n minus D, for all x in this set U, and H inverse from M intersection W to U must be continuous. Okay, so this is the parametric form of the definition. Okay, now let me just mention a function H that satisfies all the conditions of this part. Conditions of this part, this third definition, is said to be a local parametrization of M near A. Okay, it parametrizes a portion of the manifold around the point A. So before moving on to the comments about this definition, let me just give what this n-dimensional manifold sitting in Rn is going to be. In addition, so this is apart from these three conditions. In addition, an n-dimensional manifold in Rn is just an open set. Non-empty. Okay, we had taken D to be less than n in the above three criterion. In the scenario where you want to study an n-dimensional manifold in Rn, it's just an open set. Now some comments about this definition, many of which will be trivial. Notice that the smoothness class, when you say CK manifold, that is determined by the smoothness of the map under consideration in each one of these definitions. So here we had f to be a CK smooth function in the first definition. In the second one, we had g to be a CK smooth function, and in the third definition, we had h to be a CK smooth function. Okay, so that's the first comment. Typically for this course, just C1 is enough. We will usually be considering just C1 manifolds. The most important class of manifolds are C infinity manifolds. That is, these functions h, g and f, they are all C infinity smooth. So in this K is allowed to be infinity. That's another comment. Third comment is any CK manifold is automatically a CK minus 1 manifold for obvious reasons. That's the third comment. Fourth comment is this this neighborhood W, this open set W that we are considering, for notational simplicity, we have used the same W for all three definitions, but they need not be the same, obviously. Each definition could give you a different W for which the conclusion of this definition is true. It need not be the case that the W that you choose here will work for the W that you choose here. That might not happen. So be careful. This is just to make sure that we don't get overburdened with notation, that we have reused the same letter W. Okay, so now more specific comments about the definition. The first condition, as I have already mentioned, is just an overly pedantic way of saying that locally the set M looks like the graph of a CK smooth function. Now, loosely speaking, a d-dimensional manifold is an object on which we have d degrees of freedom. So this d degrees of freedom is determined by the d independent variables. Okay, so the first definition sort of models that. The second definition also models that, if you think about it. Each additional coordinate in the codomain adds on one constraint for this set, right? So this is a thing that satisfies the g of x equal to 0. That's precisely the points of this manifold. So you can think of each additional coordinate in the codomain as adding a constraint and reducing the degree of freedom by 1. Okay, so if you have n minus d in equations, then the degrees of freedom you have are d exactly. So this is another way of looking at the second definition. Now third definition, I'll have more to say about it in the examples video, which is the next video in fact. So this third condition looks extremely complicated compared to the second condition. It's modeled on the second condition. The graph obviously parameterizes this, but why have we kept such a complicated definition for when you want to consider parameterizations? Well, the reason is as follows. The reason is that there are certain things that are automatic for graphs. For instance, this x comma f of x, that's how the graph, x comma g of x in this situation, that's the graph, that will automatically be full rank, right? So you don't need to put that condition, and the inverse map will automatically be continuous because the inverse of the graph is just a projection map, if you think about it. So certain things are automatic in the graph, so you have to make that explicit when you look at the parameterization. The conditions will become very clear when we talk about examples, and you will see several exercises where what will go wrong if you drop one of these conditions. You will have figures which are obviously not going to look locally Euclidean become manifolds. Okay. Now final comment, sometimes we have a map H from an open set U to the manifold M that need not satisfy all these conditions. Okay, we have a lot of conditions. This map H need not satisfy all of this. So H nevertheless sort of parameterizes M near this point A, but it doesn't parameterize it nicely in the sense of this definition 3. But we will often have to consider such maps. In fact, what will happen is we'll have a global map to M, which a smooth map, let's say, from H from an open set U to M, that may not be full rank at all points and so on. But it might be possible to manufacture from this function H a local parameterization in the sense of this definition. So we will sometimes say that a map that takes an open set U and maps it to a portion of M, even if it doesn't satisfy all these conditions, we might still continue to call it a parameterization. So that's just an abuse of terminology. It's just for convenience. I don't want to invent a new term for that specific situation that arises so often. So I'm just going to call that also a parameterization. But we will make clear when we want to say something is a local parameterization of M near A, we mean something that satisfies all these conditions. Okay. So let's begin with the proof of the equivalence. The proof is somewhat long but not so difficult. Let's just illustrate what the rank, where the rank comes into the picture with a small lemma. With a small lemma, let f from U to V be a C1 smooth diffeomorphism from U to V. This just means that the inverse map is also a C1 map and F is bijective. Okay, of course U and V subset of Rn are open. Now if X is a point of U, then dfx from Rn to Rn is an isomorphism. Consequently, dfx is full rank everywhere. The proof of this is a triviality. The proof of this is a complete triviality. So we have F composed with F inverse is identity. So the chain rule says df inverse at a point X, and so to be ultra precise, df at F inverse X multiplied by F inverse X is nothing but the identity linear transformation, identity linear transformation, not matrix, identity linear transformation. and that's it. This completes the proof. Basic linear algebra will tell you that dfx and dfx inverse are isomorphisms. So I'm not going to elaborate anymore. This is a rather simple thing. Okay. Now, this is just to illustrate about full rank. We are not really going to use this lemma in this proof. Let's begin with the proof. We will first show, let's solve the easy cases. The first criterion obviously implies the third. I had made a comment about this. A graph is automatically going to be a parametrization that satisfies all the conditions of part 3. The inverse being continuous is just because the inverse is the projection. It being full rank is because it's a graph. This is a very straightforward thing and left to you. Okay. Now we are going to prove that second criterion implies the first. So we have to show that if it's locally the level set, it's going to be locally a graph. Okay. Now the assumption is dg at A has rank n minus k or n minus d. Sorry, dg at A has rank n minus d. Now this means in the matrix of dga we have n minus d linearly independent rows. This is just the rank being n minus d translated into matrix form. So it will have n minus d linearly independent rows. Okay. Let I1, I2, I3, comma dot 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 ID be the other rows. Okay. Consider those to be the other rows. Then the implicit function theorem says, implicit function theorem immediately tells us that in some neighborhood, some open set around A in Rn M. So let's call this we will use a different thing. Let's say V. Let's this open set, let's call it V. M intersect V is going to be the graph of a ck smooth function of x I1, x I2 dot 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 x ID. Okay, so these xi1 to xid are going to be the independent variables, and this function is going to determine the n minus d, the rest of the variables, and this set M intersection V is going to be the graph. This is just a straightforward application of the implicit function theorem. It's going to be left to you. Okay, I must mention, when you take these other rows, you take it in order. Okay, you take these other rows in order, because when we said graph, we had defined I1 should be the first, I2 should be the second. They should be in order. So you just take these rows in order, the other rows in order, and then you just apply the implicit function theorem, just check the hypothesis. This is just a matter of unwinding the statement of the implicit function and the situation we are in. It will immediately follow. Okay, so I'm going to leave the details finishing this part, that the second criterion in fact implies the first to you. The rest of the proof is rather easy. Okay, now we have to show the toughest part. We have to show that third criterion implies the second. Criterion implies the second. That is, if you can locally parameterize a piece of M, then you can write a portion of M also as a level set of a function that has all these properties that we need from criterion 2. Okay, so let H parameterize M intersection W. Okay, and satisfy all the conditions. Of the third criterion. That is, it's a local parameterization near the point A of the third criterion. Okay, we must somehow manufacture a function whose level hypersurface is going to coincide with this M, at least locally. Okay, now we know that DH first of all we assume H of 0 is equal to A. Okay, now we also know that rank DH0 is equal to D. This is part of the hypothesis of what it means for H to be a local parameterization. So what we do is we changed the basis. Essentially, this is just going to be a permutation. We change the basis in RD. So this is just by a permutation. Permute the basis. We permute the basis and assume that the first k rows of DH0 are linearly independent. Okay, the matrix, to be 100% precise, first k rows of the matrix of DH0 are linearly independent. We can do this. There will be k rows that are linearly independent. You just permute the coordinates to make those k rows the first k rows of the matrix of DH0. Okay, so in other words, the D cross D submatrix of DH0 comprising the first k rows is an invertible matrix. Again, this is just saying the same thing in a different way. Invertible matrix. Okay. Now this remark that the first k rows is an invertible matrix is going to become very important in a moment. Define G from U. Recall U was the domain of H. U cross Rn minus D to Rn. This is a map that takes the point x comma y, x is in U and y is in R minus D, and maps it to h of x, which will be an element of Rn, plus 0y. Okay, we augment d zeros and then add y, then put y in the second coordinate. So this will also be, this second part will also be in Rn, and you just add these two. Okay, so why are we doing this? Well, we want to somehow apply the inverse function theorem. The problem is dimensions don't match, so we are going to make the dimensions match by tagging on new variables n minus d of them, but we want to do it in such a way that there is invertibility, so that's why we are tagging on 0y. And it will become very clear why we assume that the d cross d submatrix of the first k rows are exactly the ones that are going to be linearly independent, because it will now be very obvious. It is obvious that dg of 0 is invertible. Please check that. What will happen is there will be a k cross k submatrix, not k cross k, d cross d submatrix, which is going to be invertible, contributed by H. Then the remaining one is sort of like identity. So I'm going to be a bit vague in this. So essentially it will be a block matrix. You can check that easily, that the matrix of this dg of 0 is going to be invertible. Just write down the matrix and it will be very clear to you. Okay. Now that we have shown that dg of 0 is invertible, or rather you are going to show that dg of 0 is invertible, we can apply the inverse function theorem. What does the inverse function theorem say? Well, we can find a small product open set in Rd cross Rn minus d centered at 0, say v1 cross v2, so v1 is an open subset of Rd, v2 is an open subset of Rn minus d. We can find a small open product open set v1 cross v2 such that G is a CK smooth diffeomorphism on v1 cross v2. Okay, so that means G from v1 cross v2 on to G of v1 cross v2, and that inverse is also going to be a CK smooth map. That's what it means. Okay, we shrink W and assume that A continues to be in W, but W is a subset of G of v1 cross v2. This can be done. We just shrink this W so that this W lies entirely in the image of G of v1 cross v2. Okay, so far we have just used the rank condition on the map F, on the map H, to get this diffeomorphism G using the inverse function theorem. Now what we are going to do is we need to invoke the fact that H inverse is also continuous. Since H inverse from M intersection W to U was continuous, we can shrink W further and assume that H inverse of M intersect W is fully contained in V1. Okay, we can do this as well because H inverse is continuous on M intersection W. So we just shrink W even further so that H inverse of M intersection W is fully contained in V1. This is just characterizing the epsilon delta definition for the continuity of H inverse. So this open set V1, you choose an appropriate epsilon so that the zero neighborhood of an open ball centered at 0 fully contained in V1, you choose an appropriate delta that will tell you how much to shrink W. Okay. Now, what we are going to do is we are going to see what we can do with this map G. We know that this map G is a CK smooth diffeomorphism. So what we do is let capital H from W to V1 cross V2 be the inverse of G. We know that H is also a CK smooth map. Let G from W to V2 be its second component. That is H, I'm writing it as two components, one that maps into V1, one that maps into V2. I'm just going to consider G to be the second component, the component that maps to G2. Okay. Now this, we are at the finishing stages of this proof. As the notation suggests, this G does the job. G satisfies all the conditions of criterion 2. Okay. How do we show this? Well, we know that dH of X is a CK smooth, not d H of H is a CK smooth diffeomorphism, and therefore this is the only place I'm going to invoke the previous lemma. DHX is full rank at all points of W. Okay. Now since DHX is full rank at all points of W, it immediately follows that rank of dg of X is exactly equal to n minus d for all X in W. This is immediate. Okay. So we have to show now that the level set of this function G at 0 is precisely M intersect W. So suppose X is a point in W and G of X is equal to 0. We have to now show that X is actually a point in M intersection W. It's also a point in M. But what is G of X equal to 0 saying? It just says that H of X is going to be of the form Z comma 0. Okay, where Z is in V1. So in other words, shifting this back, G of Z0 is going to be in is not going to be in, is exactly equal to Z, is exactly equal to X, but this is just H of X plus 0, 0, right? That's the way this map G was defined. It's just H of X plus 0, 0, which is just equal to H of X. Okay, but H maps on to M intersection W, so this means that X is in M intersection W. So that was just showing that if you have a point x in M intersection W, then g of x equal to 0. Conversely, if x is in M intersection W, then we can find z in V1 such that h of z is equal to x, right? Then h of g of z comma 0 is x plus 0y is equal to x. Consequently, capital H of this point x has got to be z comma 0, which just means g of x is 0. Okay, so what we have shown is, if you start with a point x such that g of x is 0, then this point x has to be in M intersection W. If you start with a point x in M intersection W, then g of x equal to 0. Consequently, M intersection W is the level set of G. And this concludes the equivalence of the three definitions of a manifold that we have given. Now, just one remark I want to make. I had defined a n-dimensional manifold in Rn as just any non-empty open set in Rn. Now, there is a way to write out this three equivalent conditions that does not depend on D being less than n minus 1. Okay, so for instance, you can write the open set U in Rn as a graph of a function defined on Rn, but whose codomain is R0, which is just the set consisting of the single vector 0. Now, it is a bit inelegant in my opinion to do it that way, so I am not doing that. I am just specifying D equal to n case separately. I am doing that separately because I don't want to treat graphs taking values in the set with 0 and all that. It's a bit complicated. But nevertheless, you should know that it can be done. So this concludes the proof. This is a course on real analysis, and you have just watched the video on the definition of a manifold.